Hello students, I am Saili Rathod and today I welcome you all in the video number 10 of Digital Electronics whose subject code is 204. In this today's video, we are going to start with the new unit, that is unit number 2, Introduction to Analog and Digital Signals. Up till now, that is till the video number 9, we have studied the unit number 1, which was about the number systems. In the first unit, we have studied the different types of number systems. Types of number systems like decimal number, binary numbers, then hexadecimal and octal numbering systems. Then we have seen the conversions of all these numbering systems. That is how to convert one number system to another number systems. Then we have seen the complementary theory, in which we have studied about 1's complement, 2's complement, 9's complement, 10's complement, and also we have seen how to calculate the arithmetics using this complementary theory. And lastly, we have studied about the different types of codes and the classification of different types of codes. Like we have seen the weighted codes, non-weighted codes, then the gray codes, accessory codes, and so on. So today we will start with the new unit, and the today's topic that we are going to study is Introduction, Characteristics of Analog and Digital Signals. So let's move towards the first point. What is analog signal? Before that, we will see what are the points that we are going to cover in today's lecture. We are going to see what is analog signal, what is digital signal. We will see the characteristics of analog and digital signals. These characteristics we will see comparatively. And then lastly, we will see the logic levels, which is related to the digital signal. Okay, so before going ahead, we will see what is analog and digital signals. In many instruments or in transmission of data from one place to another, a particular signal is transferred from transmitter to receiver. So previously, in the previous technologies, many times analog signals was used to transfer the data from one place to another, but there were some drawbacks of these analog signals. So a digital signal was introduced, and which is generally nowadays used for the transmission of data, and it is also easy to transfer the data from one place to another, and it is safe. So that's why many times we use still the analog signal, but comparatively digital signals are more used nowadays as compared to analog signals. So let's move ahead. Here we will see analog signals and digital signals. The first point in analog signal is continuous wave, and digital signal is in the form of discrete signal. So this type of signals we will see diagrammatically in the next slide. Why we call the analog signal is continuous? Because it is a time varying signal and the data is in the form of continuous waveform. For example, we can say a sine wave. It is an analog signal which contains a particular data, and it transfers the sine wave or the analog signal from one place to another. But in case of digital signal, it is not a continuous waveform. It also varies with time, but it is not continuously varying. It is in the form of 0 and 1, that is logic level high or low. So this type of digital signals are discrete in their properties. The second point is finite range of values. As the analog signal is continuous waveform, so to form a continuous wave, there are infinite range of values which are plotted or which are included in that sine wave or any analog signal. And in case of digital signals, the values are finite range of values, that is 2. Either it is 0 or it is 1. Third point is the more exact values but more difficult to work with. Analog signals are more exact. Okay, it means we can plot a value of 2.3, 2.4 in analog signals, but in digital signals we cannot put exact value. We only have to provide the data in the form of zeros and ones. So analog signal is having more exact values, but while practically working it is somewhat difficult to manage the signal. In digital signals it does not as exact as analog but easier to work with. Okay, it means the digital signal is not having that much exactness or accuracy, but it is easier to deal with the signals. Here we have seen an example of analog and digital signals. A digital thermostat in a room displays a temperature of 72 degrees. An analog thermometer measures the room temperature at 72.482. Okay, so here you can see how exact the analog thermometer measures. It gives the value in the form of decimal point, that is 72.482. But the digital thermometer, it only measures the value of 72 degrees. It does not gives the value after the point. The analog value is continuous and more accurate, but the digital value is more than adequate for the application and significantly easier to process electronically. Okay, so this is an example of analog and digital signal. That is how the accuracy differs in both the signals. Now in this slide we can see both the signals, analog and digital signals. The first diagram shows us the analog signals, in which we have plotted the amplitude against the time. So you can see a sine wave or sine wave is plotted on the according to the time. But in digital signal, the signal is in the form of ones and zeros, that is logic level high or 0. Here the data 100101 is plotted on the graph. So for the logic level 1 we have a square wave, but for logic level 0 there is no signal. It means it gives 0 for the 0 signal. So likewise you can plot any data on the graph for the digital signal. Now here we will see an example of analog signal. An analog signal can be any time varying signal. Minimum value and maximum value can be either positive or negative. Okay, it means like from the three waves, sine wave, square wave or random periodic wave, you can see the signal can be plotted in the form of positive or negative values. They can be periodically repeating or non-periodically. Okay, it means the value can be repeated or it may not repeat. We can plot any value in the form of analog signal. The fourth point is sine waves and square waves are two common analog signals. Mostly the sine wave and square wave, these are generally used for the analog signal transmission. In the second diagram you can see the square wave. It looks like a digital signal, but it is not a digital signal, as we know that we can represent logic levels as 1 or 0 in the digital signal. But here in the second diagram you can see the wave goes from high to low, means it gives a positive value as well as negative, that is from the lower from the middle axis. So we can recognize it that it is not a digital signal. it is a square wave. It is an analog signal, but it looks like a digital signal. It is a form of square wave. Sine waves and square waves are two common analog signals which are generally used. Note that this square wave is not a digital signal because its minimum value is negative. Okay, so as just I have explained, the negative minimum value is negative, so it is not a digital signal, it is a square wave. And the third one, that is random periodic. It means the value change as the values changes accordingly, the values plotted on the graph also changes. It is a random periodic wave in the third diagram. Now we will see the parts of analog signal. Here in this diagram we have shown a sine wave which is having the amplitude peak to peak. Here from the diagram you can see this is the amplitude from peak to peak, and this is the amplitude for peak. Means for a positive half cycle we can say the amplitude is A. For negative sine wave you can see the negative amplitude of the negative half wave. Here the period T is what? It is the period to complete one sine wave, that is from positive half cycle to negative half cycle. So we know that frequency is the inverse of time, so F equals to 1 upon T. It is measured in hertz. So it is the general parts of the analog signals. Now we will move ahead with the digital signal, but before going towards the digital signal we should know that how we put the values in the form of ones and zeros in the digital signal. So before examining digital signal we must define logic levels. A logic level is a voltage level that represents a defined digital state. Logic high, the higher of two voltages, typically 5 volt. Okay, so generally when we transfer or we record the data in the form of digital signal, for high voltage it is represented as 1 and the voltage is it is mostly 5 volts, and for logic level 0 it is obviously the 0 volts. So the first point says that logic high, which is the higher of two voltages, typically 5 volts, and the logic low, the lower of two voltages, typically 0 volts. Okay, now here you can see logic high and logic low. So in between logic high and logic low there is a part which is shown as invalid logic level. So invalid logic level, here you can see the range is from 2.0 to 0.8, and we know that in digital signals there is no value which can be represented from 0.8 to 2. So this part is shown as the invalid logic level. And here the logic high is shown for 5 volt, means from lower level to 5 volt. So we have written here logic high, and the lower value which goes up till the 0 volt. So that's why we can represent it as the logic low. The table shows us that logic level high and low. High represents the voltage of 5 volt, which is a true value, and it is generally used for on, and the value in the form of digital signal it is 1. And for the low, logic level low, the voltage is 0 volts. We call it as the false value, and it is a logic level 0 which is used for showing the signal is off. Now the example of digital signal. The digital signals are commonly referred to as square waves or clock signals. Their minimum value must be 0 volts and their maximum values must be 5 volt. Okay, now in this figure you can see the logic level starts from 0 and goes high up to 5 volts. As it looks like a square wave, but the logic level does not go below the x-axis. Therefore, we cannot say it is a square wave. It only represents the signal in the form of from 0 volt to 5 volts. Their minimum value must be 0 volts and their maximum value must be 5 volts. They can be periodic, repeating, or non-periodic. And the last point says that time the signal is high, TH can vary anywhere from 1% of to the period to 99% of the period. Okay, so between this range, the time can be represented as TH for high. Now we will see the characteristics of analog signal. Here I have shown a table. Why? Because you should know the characteristics of both analog and digital signals comparatively. So side by side you can compare the analog signal with the digital signal. So first characteristic is analog signal is continuous and time varying, but the digital signal have two or more states and in binary form. Okay, it means analog signal is continuous wave where the digital signal is discrete wave which is in the form of binary. Second point says that troubleshooting of analog signals are difficult. This point we have seen while the description of analog signal also. There we have seen that the exactness in the analog signal is more, but it is difficult to handle these signals. So troubleshooting of these signals are difficult. And in digital signals, troubleshooting of digital signals are easy. Then third point says that an analog signal is usually in the form of sine wave. Okay, we can use the square wave as well as sine wave, but generally used it is in the form of sine wave. And in digital signal, a digital signal is usually in the form of square wave, and the square wave goes from logic level 0 to logic level 1, that is from 0 volt to 5 volt. Fourth point says that it is easily affected by noise, analog signal, and the digital signals, these are stable and less prone to noise. Fifth point says that analog signals are continuous values to represent the data, and digital signals use discrete values to represent the data. Okay, as analog signal is a continuous wave, so it means the values are in the form of continuous form which are represented on the sine wave. Next point says that accuracy of the analog signal may be affected by noise. Okay, so if the signal gets affected or it includes some distortion, some noise, then the accuracy of that signal may vary from the original signal. And the accuracy of the digital signals are immune from the noise. As the value of this digital signal is from 0, either 0 or 1, so there is very less chance to introduce the noise. Next point is analog signals may be affected during the data transmission. Okay, data transmission, while data transmission, the noise may get included and the false data can also be included in the analog signal, but in digital signals they are not affected during data transmission, and many a times the signals are also encrypted, so there is less chance to include the false data in any signal. Next point says that analog signal use more power and digital signal use less power. Why this? Because the data is in the form of discrete values from 0, logic 1. So there is less power consumption in digital signals. Then the examples of analog signals are temperature, pressure, flow measurement, etc. And the examples of digital signal are valve feedback, motor start, trip, etc. So all these digital instruments use the digital signals where the data can be represented in 0 and 1, or the device can be operated on only two logic levels. Then the components like resistor, capacitor, inductor, diodes are used in analog circuits, and the components like transistors, logic gates, microcontrollers are used in digital circuits. So these are the examples of the analog and digital signals. So here, this is very important table. Here you can see the characteristics of the analog and digital signals, and this table can also be used if you are asked about the difference between the analog and digital signals. So in today's lecture we have seen the basic introduction of both these signals, analog and digital signals. In the next video, that is video number 11, we will start with the next point, that is the basic gates. So till that, keep studying and just have an overview about this analog and digital signals so that you will be able to understand the next point. So thank you so much.